India can design a supersonic fighter, build its airframe, write its flight control software, and integrate its weapons. But the Tejas still flies with an imported engine. That contradiction points to one of the hardest problems in engineering. A fighter turbofan must make enormous thrust from a compact machine, remain stable through violent throttle changes, survive temperatures that can weaken its own metal, and do all of this thousands of times. Kaveri was India's attempt to master that complete system. The original Kaveri did not become the engine of the Tejas. That fact matters, but calling it simply a failed engine hides the engineering record. 9 full prototypes and 4 core engines were built. Thousands of test hours accumulated. A Kaveri flew on an IL-76 test bed. Materials, controls, rigs, certification methods, and manufacturing knowledge were created around it. The honest story is neither triumph nor humiliation. It is the story of an ambitious requirement, a real performance gap, and a technical base that continued after the aircraft moved on. The Kaveri project was sanctioned in 1989, when the light combat aircraft was still taking shape. The goal was not merely to assemble a foreign design. GTRE was expected to develop an indigenous afterburning turbofan within the mass and dimensions available inside a light fighter. That meant solving aerodynamics, combustion, high-temperature materials, bearings, lubrication, controls, testing, and production at the same time. Every module affected the others. A heavier turbine demanded more structure. A weaker compressor reduced pressure and thrust. A hotter cycle demanded better blades and better cooling. An engine cannot be judged by thrust alone. A fighter carries every kilogram of engine through every maneuver. The inlet supplies a limited mass flow. The fuselage fixes the diameter. Fuel consumption controls range. The center of gravity constrains installation. Reliability governs whether the aircraft can be dispatched at all. The real target is a network: thrust, weight, fuel burn, response, temperature margin, life, and manufacturability. Kaveri had to meet those demands together. Making thrust, once on a stand, was only the beginning. A turbofan is a continuous energy conversion machine. Air enters the intake. The fan moves a large stream, while the core compressor squeezes part of that air to far higher pressure. Fuel burns in the combustor. The hot gas expands through turbine stages, which extract enough power to drive the compressor and fan through concentric shafts. What remains accelerates through the nozzle to create thrust. In an afterburning fighter engine, more fuel can be burned downstream of the turbine for a temporary increase in exhaust energy. The compressor is a ladder of rotating and stationary airfoils. Each rotor adds velocity. Each stator turns part of that velocity into pressure and redirects the flow for the next stage. A single stage produces only a modest pressure rise, so the gain must accumulate without allowing the boundary layer to separate. Clearances measured around blade tips, surface finish, vibration, and manufacturing variation all change the result. Compressor efficiency determines how much turbine power is consumed before the engine can deliver useful thrust. Engineers plot compressor behavior on a map. Corrected mass flow runs across one axis. Pressure ratio rises on the other. Curved speed lines show how the compressor behaves at different rotational speeds. Near one edge is choke, where more flow becomes difficult. Near the other is the surge line, where stable compression can collapse. The useful operating line must stay inside that boundary through takeoff, high altitude, maneuvers, and rapid throttle commands. A fighter needs margin not only at steady conditions, but while the entire engine is changing speed. Rotating stall begins when regions of separated flow travel around the compressor annulus. Surge is a larger system instability. Pressure delivery collapses and flow can oscillate through the whole compression system. The result may be a bang, loss of thrust, extreme vibration, or flame disturbance. Variable guide vanes, bleed schedules, and fuel control help keep the operating point away from danger. But each protection costs complexity or performance. The compressor must be efficient near its design point, and still tolerant everywhere the aircraft may demand power. Compressed air reaches the combustor moving far too quickly for a flame to survive without careful management. Swirlers create recirculation zones that anchor combustion. Only part of the air enters the primary burning region. The rest cools the liner and dilutes the hot gases before the turbine. Engineers must avoid flameout, pressure oscillation, smoke, and uneven temperature. That last quantity, called pattern factor, is crucial. A local hot streak entering the turbine can shorten blade life, even when the average temperature looks acceptable. The core of the difficulty sits behind the combustor. Turbine blades must extract work from gas hot enough to damage the material carrying the load. They spin under enormous centrifugal stress, while pressure and temperature change across every flight. The Kaveri core brought together Kaveri's high-pressure compressor, combustor, and high-pressure turbine, so that this hot-end system could be studied as one machine. Performance here is not a single material number. It is an interaction between alloy, crystal structure, coating, cooling geometry, stress, and manufacturing quality. A modern turbine blade is often hollow. Cooler air bled from the compressor travels through internal passages, strikes selected surfaces, and exits through small holes to form a protective film. Thermal barrier coatings slow heat entering the metal, but cooling air is not free. Air diverted from the main cycle reduces efficiency, and every hole changes stress and manufacturing difficulty. Too little cooling sacrifices life. Too much sacrifices performance. The design problem is to place limited cooling flow exactly where the blade needs it, repeatedly, across thousands of manufactured parts. Ordinary cast metal contains many crystals separated by grain boundaries. At high temperature and stress, those boundaries can become paths for creep and damage. Directionally solidified blades align grains with the major load. Single crystal blades go further by eliminating grain boundaries from the airfoil, but the phrase single crystal can sound more magical than it is. The alloy chemistry, casting process, defects, heat treatment, coating, cooling passages, and inspection must all work together. Producing one good blade is different from producing every blade within a controlled process window. The Tejas decision came down to integration reality. In the configuration examined by the controller and auditor general, Kaveri weighed about 135 kilograms more than the cited target and produced 70 kilonewtons against an 81 kilonewton requirement. Those are dated audit figures, not a claim about every later test article, but they show the coupled problem clearly: less thrust from more mass. The aircraft program could not wait indefinitely for compressor, turbine, control, and reliability work to converge, so Tejas continued with an imported engine. By 2021, official figures listed 3,217 hours of Kaveri engine testing, along with completed altitude and flying testbed trials. Test hours matter because failures expose what analysis missed: vibration modes, seal behavior, thermal distortion, all system transients, and control interactions. But a test campaign does not automatically equal an operational engine. Certification requires a defined configuration, repeatable hardware, demonstrated life, and evidence tied to an aircraft duty cycle. Kaveri built significant test experience while still falling short of the fighter installation it began with. Full Authority Digital Engine Control, or FADEC, turns the pilot's command into fuel flow, variable geometry, and protection limits. It watches shaft speed, temperature, pressure, and actuator position. It must accelerate the engine quickly without crossing surge or temperature limits, and it must respond safely when a sensor disagrees. India reported designing, developing, and qualifying an indigenous FADEC through the Kaveri program. That is a meaningful capability. Yet software, electronics, sensors, actuators, and the physical engine must be qualified together, because control logic cannot rescue hardware with insufficient aerodynamic or thermal margin. The program created more than complete engines. Official reporting credited it with type-certified indigenous materials, digital control work, altitude testing, flying testbed experience, and higher readiness in several critical technology domains. Around those achievements sit less visible assets: engineers who have seen real failures, suppliers familiar with aerospace process control, instrumentation, data systems, and certification practice. None of this erases the Tejas shortfall. It explains why the program's value cannot be measured only by whether one engine entered one aircraft. Complex capability accumulates through hardware, people, facilities, and data. The dry Kaveri derivative removes the afterburning requirement and aims at a different aircraft mission. In July 2025, the Ministry of Defense identified the Kaveri derivative engine as the power plant for a remotely piloted strike aircraft and listed separate sanctioned projects for flightworthy development and technology demonstration. That does not make the derivative a fighter engine, and it should not be presented as one. It means a core developed for Kaveri can be adapted where non-afterburning thrust, endurance, and installation requirements create a different engineering trade space. A prototype proves that a design can exist. Production proves that the process can repeat it. Powder chemistry, forging history, casting defects, machining, coatings, hole geometry, balancing, and inspection all create variation. A fighter engine must tolerate that variation without losing thrust, life, or stability. The factory therefore becomes part of the design. Drawings need measurable limits. Suppliers need controlled special processes. Every nonconformance needs a disposition backed by engineering evidence. Sovereignty is not achieved when one engine runs. It is achieved when the next engine behaves like the first. Kaveri 2 is useful as a documentary title, but it should not be mistaken for the official name of one cleanly defined program. A genuine next-generation core would need higher compressor efficiency and pressure ratio, stronger surge margin, more uniform combustion, higher temperature capability, better cooling, modern control electronics, and production repeatability. These advances must arrive together in a lighter engine with greater life and thrust-to-weight ratio. Replacing a module may improve one limit. Building a competitive fighter core requires the entire thermodynamic and industrial system to converge. 3 ideas must remain separate. First is the Kaveri technology base: knowledge, rigs, materials, controls, and test experience. Second is the Kaveri derivative, adapted for a non-afterburning unmanned aircraft role. Third are future high-thrust fighter engine programs, which may use capabilities born in Kaveri but would require a new level of core performance and industrial execution. International collaboration may accelerate that climb. It does not remove the need for Indian engineers to own requirements, design decisions, validation data, manufacturing processes, and configuration control. Fighter engines are difficult because every advantage creates another penalty. Higher temperature can improve specific thrust but attacks turbine life. More cooling protects blades but steals compressed air. More stages can raise pressure but add weight, length, and modes of vibration. Tighter clearances improve efficiency but risk rubbing during thermal distortion. Faster response helps combat performance but reduces compressor margin. The machine operates near aerodynamic, thermal, structural, and manufacturing limits at once. Mastery is not a secret component. It is the ability to manage thousands of coupled compromises through design, test, and production. The original Kaveri did not deliver the Tejas engine that India set out to build. It also did not disappear. Its cores, tests, controls, materials, and failures became part of India's propulsion base, and its dry derivative now follows a different path. The next fighter engine will be judged by a harder standard than a prototype or announcement. It must produce the required thrust at the required mass, survive its duty cycle, remain stable in the aircraft, and be manufactured repeatedly. Jet engine sovereignty is not a moment. It is a system that works again and again.